Viewers like you make this program possible. Support your local PBS station.
For as long as humanity has gazed up at the sky, we've wondered, what's out there? Are there any other worlds like ours?
We knew very little about the solar system before we started sending spacecraft there. The outer planets were just tiny points of light. We knew very little about them, and much less about the moons in orbit around them.
But in the 40 years since NASA's Voyager missions began their grand tour of the outer planets, we've made huge leaps in space exploration. We've sent rovers to explore Mars, discovered volcanoes on distant moons, and found frozen worlds that hide oceans beneath thick crusts of ice. Features and processes once thought unique to Earth are turning up all over the solar system, and there's a growing optimism that one day we will find life somewhere out among the stars. More and more, that search for extraterrestrial life is driving exploration. Finding it would revolutionize our understanding of our place in the cosmos.
Copernicus completely revamped our views about our universe when he postulated the sun and not the Earth was at the center of the solar system. Darwin announced that all of life on Earth, including humans, came from a common root. And now we are searching for evidence that life began and evolved somewhere other than Earth. A completely independent second genesis. And to find it would force us to rewrite the story of life.
NASA's Voyager missions were an epic drive-by of the outer planets. Carolyn Porco began her career on Voyager, helping to transform our understanding of the solar system and unravel the mystery and beauty of the gas giants and their moons. In 1990, she was selected as the lead imaging scientist on a next-generation NASA mission called Cassini.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini has been orbiting Saturn for the last 13 years, gathering data and beaming back spectacular images of the planet, its rings, and many of its 62 moons. Carolyn was initially fascinated by the interactions of the rings and moons. But a major discovery in 2005 pushed her toward the search for life.
We had planned to take a close look at Enceladus, which is this tiny moon in orbit around Saturn.
What Cassini revealed was spectacular.
In November of 2005, we saw dozens of geysers coming from Enceladus. Narrow, spiky-looking jets of fine, icy particles erupting from the South Pole.
Enceladus, a moon less than 500 miles around, and because of its icy surface, one of the brightest objects in the solar system. And in the southern hemisphere, mysterious fractures nicknamed tiger stripes, the source of the watery jets, and a link to a liquid ocean beneath the ice.
Once we found the geysers and knew that they were coming from liquid water, I realized this had tremendous implications for the study of life elsewhere in the solar system.
Tremendous implications, because liquid water is considered crucial for life. And that made Enceladus an alluring candidate as a home for life beyond Earth.
I kind of did a pivot. I just started to throw myself into the study of Enceladus.
The search for life on places like Enceladus, Mars, or Jupiter's icy moon Europa, represents a new wave in space exploration. But the quest is still rooted in what we know about the history of life on Earth. Today, life is rich and varied, found almost everywhere, in wondrous forms. But only in the last 500 million years or so did it begin evolving into the animals and plants we now know. Before that, for some 3 billion years, the planet was teeming with life that came in only one size: microscopic. Because microbes were the first forms of life to appear on Earth and have endured for billions of years, scientists believe they are our best bet for the size and shape of life elsewhere in the solar system. But they're not the easiest creatures to find. Carolyn is meeting with evolutionary biologist Andy Knoll, who studies ancient life on Earth and the clues it left behind. He's also helping guide NASA's rover teams as they search for evidence of ancient life on Mars.
So what do you actually do in searching for early life on Earth? And how does that translate to Mars?
It turns out when you look outside, you see plants and animals, these conspicuous forms of life. Those are evolutionary latecomers. Most of the history of life on Earth is microbial. And over the years, we've learned how to search successfully for both physical and chemical signatures of ancient microbial life on Earth. And once you learn how to do that, then it's a fairly easy matter to export it to Mars. Let me show you an example. So what you're looking at here is this so-called stromatolite, and we see these wavy laminations which actually represent microbial life that trapped and bound sediments and built up this reef-like structure. This particular specimen is 2.7 billion years old, and it is an unambiguous signature of life on Earth.
Okay, very interesting. So this is what you refer to as the physical remains or the physical evidence of life. But then you said you're also looking for chemical evidence. How do you do that?
Okay, well, all life that we know of is cellular. All cells that we know of have DNA and RNA, which are the information library of the cell. That doesn't preserve very well. Cells have proteins that do the structural work and enzymatic work of the cell. They don't preserve very well either. But then there's a third constituent called lipids, which make up the membranes of cells. And membranes actually separate the cell from its environment. And the good news there is that some lipids actually preserve very well in the geologic record.
How do you find those molecules?
Well, as sediments accumulate on the seafloor, organic matter will get buried with those sediments. And if you extract that organic matter, you'll find lipids. And those lipids can be related to the types of organisms that made them.
These lipids, preserved in rocks nearly 2.5 billion years old, are signatures of life. In this case, evidence of early life on Earth. Jump to Mars, where Andy and the rover team are looking for exactly the same thing.
One time in its history, Mars had bodies of water on it. We don't know how long those bodies of water lasted. So where on Mars are you going to look?
Really, it's a matter of saying, where was there water? Where did that water result in sedimentary rock deposits capable of preserving a signature of life? And can the rover get there? I mean, in some ways, we're in the golden age of Mars exploration. We have found rocks that are capable of preserving various physical and chemical signatures.
Right.
We actually have instruments that can detect organic molecules. What we have not yet found is any strong, biosignatures.
They'll keep looking, and someday soon, astronauts could join the search. But in the meantime, Carolyn is pushing for a shift in focus to Enceladus. There, they can have access to water that is still flowing, and search not for fossilized evidence of life billions of years old, but for signatures of life that could be living right now.
Those of us interested in water and places like Enceladus, we're in a different position because we're not going to be picking up rocks. We're looking at it completely from the chemical point of view.
That's the beauty of Enceladus. The plume is offering free samples of the liquid ocean to anyone who stops by. What those samples contain is the billion-dollar question, one Cassini made a valiant first attempt to answer. Soon after the plume was discovered, the team reprogrammed the craft to fly right through it.
In today's news from Saturn, a NASA spacecraft is flying through some geysers on one of the planet's moons.
Cassini's instruments managed to return information about the content. Water vapor and carbon dioxide and methane and simple organic compounds and even ammonia were found in the plume.
These simple chemicals were present and necessary for the formation of life on early Earth. Enceladus is now 2 for 2. It has a liquid ocean and the right starting materials for life. And further analysis of the samples revealed another exciting surprise.
When my Cassini colleagues analyzed the particles in the plume, they found microscopic particles of silica. And this is very good indication of hydrothermal vents, because at hydrothermal vents you have hot, mineral-laden fluids being injected into the cold ocean. And these particles like silica get carried from the bottom of the ocean all the way up to the base of the ice shell, and they get forced out the fractures. And so this is how we know there are likely hydrothermal vents on the seafloor of Enceladus.
This was a find with exciting implications. On Earth, deep-sea vents support life. In fact, entire ecosystems of strange creatures get their energy directly from the vent chemicals, or by eating those that do. At NASA's Jet Propulsion Laboratory in Pasadena, planetary chemist Lori Barge is investigating how the chemicals spewing from hydrothermal vents fuel life, and whether they could be involved in creating it.
Aha, so this is famous chimney.
Yeah, so this is where we simulate the hydrothermal vent injecting through cracks in the seafloor. And then this is your ocean, which contains anything that would be reacting with this fluid.
So that's a simulation of what could be happening on Enceladus.
Right, exactly.
The simulations test how the chemicals interact with each other in the seawater, and how different combinations produce different results.
Vents are more than just the chimney itself. It actually has all this sediment around it and underneath it. And that sediment is also very reactive because it gives you a lot of surface area. So when you have this pile of minerals, all those mineral surfaces are available for reacting. That stuff can come up, and if it can interact with mineral surfaces, then it might be able to concentrate and make things like amino acids or maybe nucleotides.
These are the building blocks of the very large molecules, proteins, DNA, and RNA, that govern life as we know it. While Lori and others are trying to create them in their labs, Carolyn is thinking bigger and farther afield. She wants to hunt them down in the wild and believes she knows just where to look.
Enceladus checks all the boxes. It's really no more complicated than that. It has liquid water, it has abundant energy, it has organic compounds, it even has evidence for hydrothermal activity at the bottom of its ocean.
Jupiter's moon Europa is also a good target. Beneath its icy surface, the moon is believed to conceal a global ocean twice the volume of Earth's. NASA recently approved a new mission to explore it. But the moon poses some serious challenges.
Europa is embedded in Jupiter's very intense radiation field. It's nasty and it can quickly destroy organic materials and even eventually the spacecraft that you send there to find them. And in the meantime, Enceladus is spewing its ocean into space. You fly through it and you can just do tremendous things. If you could land on its surface, you could do even more.
For Carolyn, a return to Enceladus is not just wishful thinking. Competition for NASA dollars is fierce, but she and her colleagues recently submitted an official proposal to do further testing of the plume with a more advanced orbiter. After that, she's hoping for a lander and has been working on 3D visualizations of what these missions might look like.
We already know where would be the best place to land.
Okay.
And that is in this other picture that we took.
Okay.
You could see the geysers are very jam-packed there. Okay, very close together.
That's what I would think, right? You'd
You
want to
could-
get right in the middle of the valley.
That would be lovely.
Yeah.
Really, but even just getting in the vicinity
Okay.
of these fractures would be good because you have material just falling on you.
The orbiter would carry instruments far more powerful than Cassini's, able to sniff out life itself or detect the chemical biosignatures life leaves behind. The lander would do even more, gathering samples of larger particles that fall back to the surface, like snow.
Material from the plumes, which means, of course, material from the oceans, which means materials from in and around the hydrothermal vents. And that's what makes this so exciting. All you have to do is just stand back and look at the big picture and think about the magnitude of the questions we're trying to ask. We could find life.
Such missions, if they're approved, are still at least a decade away. But Carolyn and her colleagues are charging ahead, undeterred. A decade means nothing when the stakes are this high.
Anything we find at this point just pushes us all that much closer to understanding life's origins. Right now, all of life we know of happens on this one planet. And our planet has gone hog wild with life. But it's all based on one root. That's one biochemical recipe operating on one small planet in one small solar system in the corner of one ordinary galaxy. So the chances are excellent that there is life somewhere else, and finding it elsewhere, anywhere, just once, in any form, would finally be proof that we are but one of many manifestations that life can take in the cosmos.